move all these things to one side. So this will be 1/2 f of x plus 1 plus f of x minus 1 minus 2 f of x equals 0. Okay, so it should look something like 1 minus 2, right. So I have minus 1, 1 minus 2, 1, zeros, 0, 1, minus 2, 1, zeros. And at the end I'll have 1 minus 2, 1, and then 1 minus 2. Right. This times f1 to f1 minus 1 equals, alright, I have zeros everywhere, except here I should have minus f of 0 over 2. Just from if you plug in x equals 1, I'll get one term. Well, I get 0 and like minus 1/2. Okay. So this is the linear algebra problem that I have to solve. And okay, but this is actually really easy to eyeball. If you just look at this relation, this is actually saying f of x plus 1 minus f of x equals f of x minus f of x minus 1. It's just saying every step has to have the same size. This is just linear. So this is just f k equals k over n. Okay. This tells you that your probability of exiting from n just depends on the linearly on your distance to the 2 points. But something that you can think about here is we're already starting to see, okay, so the punchline is that these exit problems are related to partial differential equations of the Laplacian, right? And this is kind of your standard finite difference approximation to your Laplacian. So we're already approximating, our stochastic process, right, where we exit and we look at the probability of exiting is already going to be, like the solution for this is already a solution to some approximation for our continuous type equation. But we'll go into it more in a few minutes. Alright, so let's alter this game a little bit to make it slightly more interesting. So instead of just measuring the probability when I exit, suppose I put some generic reward on exiting. So maybe I don't just get n dollars when if I hit n, I'll get some g of n dollars, and then if I get 0, I'll lose or gain g of n. G of 0 could be positive or negative. There's some rewards. G of n when hitting n first, and g of 0 and hitting 0 first. Now we want to know what's the expected reward. Starting at x. Right, so I'm using this x also for the expectation. It's the average starting at x of g of s, g of st. So what's the expected reward when I exit? And g is being specified on my boundary at 0 and n. Okay. Well, this is actually, if I look at it, the recurrence is exactly the same. Everything's exactly the same except for the boundary conditions, right? F of n now is just g of n, and f of 0, g of 0. So this sort of thing solves the same kind of recurrence. So we have the same matrix, but we have a different right-hand side. Let's call this is 1/2 L. So we have 1/2 L times our vector f equals, well, everything was 0 except we have minus g of 0 over 2 and minus g of n over 2. Okay, so now the solution isn't so obvious. Okay, well, this should just be linear interpolation, right? Same thing. Right, same thing. Okay, anyway, so the same structure kind of holds for this kind of problem. So already it's kind of starting to look, L is some kind of differential operator. This is supposed to be boundary conditions. So it's a little different. This is kind of like our Dirichlet operator, taking functions as boundary conditions. Anyway, alright, let's not worry about that. So, one more problem. We have two more problems I want to consider generically. So now, we're looking at what happens at the place of exit, but now we'll ask questions about time of exit. So we want to count the expected time it takes to exit from this region. And you know, it could be kind of tricky because if you were to just count the probabilities combinatorially, you can spend a lot of time going back and forth before you end up hitting the boundary. So to compute the distribution combinatorially is kind of a pain, but it can be done. It's not that bad. But we have the same kind of recurrence, so we can set up the same kind of problem using Markov property. So again, we'll just the 1/2 chance of going left, and then what happens? You're starting at x plus, or okay, so if you go left, then you start at x minus 1. We're looking at the exit time from x minus 1, but you took one step. So you have to add 1. So we took one step, we added 1 time, now we're going from x minus 1. And you do the same thing, x plus 1. So now, it's very similar. F of x equals 1/2 f of x plus 1 plus 1/2 f of x minus 1, now plus 1. So this is the only thing that gets added here. So now we have something that looks like, what do I say? So we'll rewrite it as 1/2 f of x plus 1. So we want to get this kind of looking like the operator we're going to be interested in later. And then at time 0, okay, if you start at 0 and n, then you take no time to stop. So f of 0 equals f of n equals 0. Okay, so we keep getting this expression, and I said that this is kind of like a finite difference operator. But for someone that doesn't work with PDEs, that's not going to be much at all. So, you know, but everyone knows difference quotients. Everyone deals with difference quotients when they teach their kids, right? So there's some familiarity, but maybe not second order. So let's do a calculation right here to see exactly the mechanics of this difference. So suppose we have some f's, nice two derivatives. I don't know if this is the best way to do it, but this is the way I was thinking last night. Let's just use fundamental theorem of calculus and hammer this calculation to see if this is similar to some kind of derivative, some higher derivative. So f of x plus 1 minus f of x minus 1 minus 2 f of x. Okay, you can already see this. The difference is like a first order one, f of x plus 1 minus f of x. Then you're like subtracting the difference on the right. You have the difference on the right minus the difference on the left, so it should be kind of like two derivatives. But, alright, I have this calculation already, so I might as well do it. So this is exactly your integral of f prime of x plus y dy this is an f of x plus 1 minus f of x, and this is an f of x plus minus f of x minus f of x minus 1. Gives you this one. Okay? And then, write this. Again using thermal calculus. It's this double integral. And then by changing the order of integration, 1 minus the f double prime of x plus z dz. Okay. So here we have an f double prime, but the thing to notice is this is something set around 0, right? And it has an integral 1. So this is like a, it's not smooth, so you don't want to call it a modifier, but it's something that integrates to 1 and is set around 0. So you could say that this is like an average of f double prime around x. Refined, and actually it would be getting closer and closer to f double prime by dividing by, we did f of x plus epsilon, x minus epsilon over epsilon squared. That would give us better and better, smaller and smaller averages. Okay, so this is really an approximation for the second derivative. That's our favorite differential operator, PDEs. So all the equations we talked about are some sort of discrete versions of this called Dirichlet problem. If you ever study PDEs, it's the first thing you ever study, because it's one of the most classical problems in partial differential equations. Minus Laplace u equals f, u on the boundary of some domain equals g, where f omega is some open set in Rd, and g is some kind of function on the boundary. Continuous in the boundary of the set, and f is nice in omega. I don't even want to worry about what it should be. Okay, so this is the general problem that we were kind of solving. Okay, we were doing it in one dimension, so the boundary was really simple. Everything we did works exactly the same, at least in the discrete case, on more dimensions than one. So we were to, how do I want to set it up? Let me go over it down here. Okay, so we were to let omega, let's say, t greater than 1, omega, some connected set of points in CD. Connected, I mean, you could always take a walk, along adjacent points, going up, left, right, down, in, out, blah, fourth dimension, whatever you want. And you can get around through the whole thing, okay? So some connected set of points is ZD. So you define boundary omega to be points in ZD without omega, but the distance from x to some point y is 1 for some y and omega. So just outside our domain. Then Sn, let's say x1 through xn. For now, xi is a random vector with IID. This kind of goes without saying. Probability that xi is plus or minus ei should be 1 over 2d, so that we have an equal chance of going every direction. So we're doing the exact same thing. And t is the first time we hit the boundary, cumulative of n such that Sn is in the boundary. Right. Then we'll get the exact same problems that this thing will solve. If g defined in the boundary, expected value starting at x of g of s t solves, well, we're going to get a, I don't want to mess up my sign, but let me write it out. Let me just write this out. Sum of f of y minus f of x, f of x. So I'm taking differences over all y minus x equals 1. So this is, before we had, you could go up, you could go left or right, now I can go in all these different directions, and so this is the kind of sum you have right here. This is kind of like, this is your graph of Gaussian, because this is how you got to define it, because it's a continuous case, so this is how it makes sense on the graph. And then f on the boundary of omega equals x. Alright, so in this, I mean this equals 0. Alright, so the sign doesn't matter because I have 0 on the right hand side. But here, this is like your higher dimensional version of this thing. We got this d that we might not want because we have so many choices that we're only stepping in one of them at the same time. We're not taking a jump in every single direction at the same time. But that's easy to get rid of if you want to. Okay. And the same thing goes with the stopping time. We could do the same kind of, this operator equals minus 1 or 1, depending on the sign. Okay, so we here right now, we're solving discretized versions of PDEs exactly using random walk. The last kind of example is, yeah.
So, like, is that the systems of equations always have solution for all trees? Suppose that you have like.
Yeah, I think that matrix I drew earlier was invertible. I'm pretty darn sure. The one I drew earlier was invertible. And so the matrix I drew earlier was, I mean, now we're working with a lot more points because, okay, so if we were working at an interval length n before, now we have an n to the d cubed, we have n to the d, like interior points, so we have n to the d equations. So this linear algebra problem is growing exponentially in the number of dimensions for a fixed diameter of the domain, but it's the same kind of structure in the matrix.
But what I'm thinking about is that you have an extremely low dimensional domain omega, and but in a really high dimensional ambient space, then the boundary data is like somehow like
the same size as the set, you mean?
Then the boundary data would be like, suppose you have a line, but it's embedding R3.
Right, so there's
a lot more boundary data.
It's about the same. Right, there's a lot more boundary data. You're right. But what do you need here to make this reasonable? fact, these equations are just telling you the value. I mean, if you just took a line, then you're not really solving anything. F of x is just a function of the ones around it. Okay, so there's one point you have to solve. You have all the ones around it, right? We're doing like this, let's say. We're walking along this line. Here are our boundary points. So this point is some function of these plus this. And this one,
Right, the theater's like the deal for determinant, right?
yeah. I mean, from the linear perspective, it seems like it should be. But actually,
But you,
I think it's not, because what's going to end up happening is we're just going to have each of our vectors on the right-hand side are going to be some function of all the boundary points. You know, some function of some number of the boundary points. Maybe it's worthwhile writing what the system is for this. But okay, this is kind of messy.
If it actually happens that the matrix is not invertible, what does it mean in the sense of hour and a walk? I mean, does it actually could
It doesn't
make
seem
make some
reasonable.
sense?
No matter what you set, there should be an expected exit time. So
I mean, if our set is not bounded, then maybe.
okay, so if the set is not bounded, right, then
Yeah,
I'm not
but
gonna
like
do
I
that.
mean that if set is bounded and every time you have some, so you need exit at some point, so you have some probability of exit at each point, then this matrix should be invertible.
The matrix is never going to have a problem being invertible. You know what the problem is? I think you're thinking that the right-hand side I wrote is not a, you don't have one point for each guy in the boundary. You have, the elements are some function of the things in the boundary. The equation over here, right, doesn't just depend on one thing in the boundary. 1D it did, right, for potential. Here it's all these things in some linear combination. So you just have one equation for each point inside the domain. And, I mean, is this still not clear? Okay. I could try to write some equation. So, see, what are the equations for something like this? Let's, I don't want to put one on everything. So let's say we're looking at points x, 0, x between n and 1. This is our domain, right? So boundary will be 0, 0, 0, n plus 1, right, let's say 0, n, and x1, x minus 1 for x and 1. Okay, so this is our boundary data. So we're going to call this g of x1, g of x minus 1, and then g of 0, 0, and g of 0, n specified. So what are the equations going to look like? It's going to say that f of 1, 0 can equal 1/4 thing above it, so we have g of 1, 1, g of 1, negative 1, g of 0, 0, plus f of 2, 0. Okay. So what does the matrix look like? The first line of the matrix will look like this. We'll have 1/4 out here. We have 1, maybe I'll have a 4, minus 1. And on the right hand side, all I have is some combination of these things. question. The question is, does there always exist a solution? And well, I don't see why not. I mean, this thing just, it's not like for each thing I have a new, like not like dimension problem. For each point in my domain, I have a equation. Okay, so maybe this is worth thinking about more because clearly there's something bothering us. Yeah.
Well, I mean, isn't this the construction of the solution though? You're not saying if we can solve this, then this expected value, like the expected value we didn't define as the solution to this system.
Right.
We defined this in some funny probabilistic way, and then
Expected value is
and then
okay.
we just said, look, it's it does solve this, right? So this is a construction of the solution, right?
For the equation, right. This is a solution for the system. I guess, yeah, I think whatever the issue was, that's lost on me now. Now I'm just blabbering on, so I'm gonna move on. Alright, so that was fun. Hope we all enjoyed that. Okay, so let's start making our way towards the heat equation. Now that we're tired ourselves out. So F is going to go from Z, D to R, and Hn of X is going to be expected value F of Sn. We want some kind of, the difference equation for Hn as a function of n and xn. So we're not looking at, we no longer put boundaries down, we're no longer looking at exit time. Well, once we fixed the exit time, we got rid of time out of the problem. The problem became a function of just position inside a domain. Now this is a function of position and time. So we do a similar sort of thing. Hn plus 1 of x is expected value f of Sn plus 1. And so what we do is we condition on what the first step was. Okay, so we say, all right, I'm not going to look at where am I in n plus 1 steps and look at f afterwards. I'm going to take a step, change my initial condition, and look at n more steps. So this is going to be the probability of taking any one of these different starting steps is 1 over 2d. And we're going to look at the expected value is starting at y for all y that have distance from x equal to 1 of f of Sn. We decreased our number of steps by 1. We took our first step. Now we're going to start the process there with n more steps. Okay? And now, okay, what do? We related this to h of y, hn of y. So this is 1 over 2d of hn of y. So now what we're going to do is subtract hn of x on both sides. We'll write this, put this into the sum to get the same kind of operator we had before. Now we divide all by 1 over 2d, and then we add it up 2d times, right? And this is our discrete time step, say time difference notion. Our spatial Laplacian approximation. And so this is kind of like dth. This is if you took a really crappy step size and we're trying to solve dth equals 1 over 2d Laplacian h using finite differences. This is exactly what you do. This is if you took step size 1. I mean, this is like the dumbest thing you could possibly do to try to solve a PDE. So numerically, you do something like this. It's been around. Time to go in there. But okay, we want to move to the continuum. That's kind of the goal of this. And so now we have to see, all right, I want to get this thing from this, so I got to think about what's the right way to scale. And there's two ways of thinking about it, but we're going to go with the approach with how do I scale my time steps and my spatial steps to turn this actually into the heat equation. What's the right scaling that if you wanted to do the finite difference approximation and get a more refined approximation, what do I have to make my difference in time? What do I have to make my difference in space? And so anyone that's studied Brownian motion, this, or even PDEs, this is beating us to death. Like, we have to know this. But the answer, well, for a time derivative, okay, we want dth. That's easy. Everyone knows how to approximate using a difference motion. This is just h of t plus delta t of x minus ht of x delta t. This is the thing that should go to dth. And then if we want to do, this is the difference with 1. I want to get the 1 over 2d Laplacian. We use ht of x plus, I want to make sure I do this right. Yeah, I'll write it like this. Delta x ei plus ht of x minus delta x ei minus 2 ht of x over delta x squared. This is the right scaling to get us two derivatives in the other direction. H of t of x. So you want your step size is delta x, right? Then you're in space, and your time space is delta t. In time, then we need to divide this one by delta t, and this one by delta x squared. And so the thing to do is say, okay, delta t should be proportional to delta x squared, and then I'll just step with, I'll take jumps at time delta t, and then my jumps will be of size delta x. Okay? And then that should be the random walk that'll, in the limit, should give me the answers
So
to these
just
kind of
intuitively, the idea is that at the rate at which we are shrinking time, no, the rate at which we're shrinking space should be like less than the rate at which we're shrinking time.
Yeah, I mean,
If
the
we're
idea is
like
it takes
central or-
it takes me a certain amount of time to hit a certain space level, and this is the right way to balance because, okay, if I want to go a distance n, it's going to take about n squared time to hit it because I'm going back and forth. I'm canceling myself so much that that's kind of what this calculation roughly tells me. I'm looking at it through the PDE perspective to tell me what I should do with my random walks, but you could just do it directly with the random walks and see the right way that it scales so that you get something in the limit. It's kind of a big thing we do in PDEs and probability is seeing how things scale in equations so that it tells you like how length should compare to time generically. That's kind of what this is saying. Okay. As a remark, before we continue, I should look at the time. 6:35. Okay, I'll try to make this fast. From a computational perspective, we were kind of done before, because you can't simulate random walks. You can't simulate continuous random walks. You simulate discrete random walks at the right scaling, so that they approximate a continuous thing. And you can't solve, unless you can solve it explicitly by hand. Numerically, you can't solve a PDE. You just solve something like a finite difference scheme. So what were we doing? We were showing how you can solve an approximation to the PDE using probability rather than linear algebra. So if you wanted to, if the goal was to use probability to numerically approximate solutions to PDEs, this is kind of the end of the story. PDE that turned into a finite difference problem, and rather than linear algebra, we chose to solve it using probability. And I was thinking about it last night, like why would I ever want to solve a problem using probability rather than linear algebra? Linear algebra is so sweet and easy, but there's a problem. It's not so bad actually, because the matrix we wrote was pretty scarce. But in general, there's a problem where the number of equations that we have to solve with this finite difference problem, if we fix a domain size, right, the diameter, is growing exponentially. We have exponentially more points inside of our grid. I mean, the matrix was rather sparse, right? So it's not so bad to compute it, but the probability doesn't actually suffer so much from the dimensionality problem, because what do you need to do? First, you need to get the average, right? So the average doesn't have anything to do with the size. It just has to do with law of large numbers, convergence rates for law of large numbers, right? It's how many samples do you need to approximate the average? And this is something independent from the dimension. This is just going to depend on your variance of the thing you're calculating. We were just calculating the expected, like some average over the boundary. As long as the function was bounded, there was no kind of growth in this, right? And then there was the time of the random walk. But the time of the random walk also doesn't scale so badly for a fixed size of the matrix, size of the domain. So this kind of scales better with dimension. Or at least it scales pretty well with dimension. And at least from a naive perspective, this scales exponentially. With dimension. But I don't know about solving equations with sparse matrices, so I really can't speak for how good these actually compare in practice. I don't know if people actually use this for it. But I use this all the time from a theoretical perspective. It's nice to have probability, or what we call stochastic representations for our solutions, because sometimes it makes this, like a lot of results like really easy to prove, and it also provides us kind of like a particle description for a lot of equations that usually are not thought of that way. What were we think? How could we think of this result that we had with the heat equation? You could say that heat. How do we like to think about heat flow? I mean, things go from hot to cold, right? So things kind of average out with the flow of heat. But we can think of it. The way we can think of this using the random walks is that there's like a heat particle sitting here, and the way heat moves is by all these heat particles bouncing around randomly, and over time they kind of just distribute themselves. So normally it's hard to think of heat as a particle thing. Differential equations don't have point mass. I mean, these differential equations don't have like point masses, but this kind of average of the exit time of the random walks gives us a sort of kind of heat flow perspective of like particles, right? Like heat particle perspective. For me, it's always helped me think about partial differential equations having this sort of particle kind of description. Okay, so quickly get to the continuum description. We have our scaling now in our back pocket. We know what we want to do. So we define WT epsilon to be, we want our steps to be, if those depths are epsilon in space, then and we want our time, delta t, to be epsilon squared. So here, spacing between the xi's is now epsilon. This is like epsilon x1, epsilon x epsilon squared. What do I want to say? Alright, so actually I want to write it like this. 1 over epsilon. So our step size is epsilon in space, and then epsilon squared in time. Okay, so I'm going to multiply by root t, divide by root t here. And then the thing to notice is that this thing, right, is going to converge to an n0, 1 random variable. This is normally distributed. Mean 0, variance 1. Why is that? Well, okay, so the xi's were plus or minus 1, probability 1/2. Okay, so their average was all 0, and the variance, which is just the expected value of the square, well, the square is just 1, so the variance is 1. They're independent, so you just add up the variances. So the variance is this thing is t over epsilon squared approximately. I have this floor. But you divide Sn over the standard deviation. This is the thing you do for the central limit theorem. Okay. This is by central limit theorem. That's at the heart of any kind of scaling of random walks to get a Brownian motion. There's going to be some kind of central limit theorem result, because that's why Brownian motion is so interesting in some sense. It's because it arises from all sorts of different walks. All sorts of different walks, if you scale them right, as long as the jump sizes aren't too crazy, they have finite variance, you're going to end up with, with the Brownian motion. So the thing to notice, okay, what is a Brownian motion? So this is like a fixed time. Okay, so I'm multiplying by root t, so it's going to be a normal random variable with variance t. Standard, if you multiply by a constant, the variance gets squared. Things to notice. I did a fixed time convergence in distribution. So all I meant is this thing behaves like a Brownian motion. It doesn't pathwise exactly converge to a Brownian motion, because I'm kind of shifting everything down. But what you can say is that the distribution of the paths is like a Brownian motion. So the statistics of anything you say about kind of a Brownian motion are going to be like the statistics of the random walk. Like if I ask the statistics of the exit time, what's the distribution of the exit time from the domain? If I resolve the domain really well with the random walks, and I want to ask that question about this limiting thing and the original thing, they're just going to converge nicely. So we have a stronger convergence of paths in distribution. And a lot of nice things come out of this. Wt minus Ws, okay, is independent of Wr. Okay, I didn't say what W is, so this is going to converge to Wt. Fix for each t, this converges to some Wt. It's converged independent of Wr, for R less than or equal to S. So, okay, I walk a bunch, and then I stop, and then I walk. It doesn't matter what I did before. My new walk is like a brand fresh new walk. Okay. Wt minus Ws is normal, mean 0, variance t minus s. That just says that if I subtracted a whole bunch of the starting with my random walk before, right, it didn't matter. It was like when I started the walk after some number of variables, I could throw away all the change from before. continuous. Okay, so this is called so the important thing is really just that the Brownian motion came out of a bunch of symmetric walks. So the only thing we're going to use for the rest of the talk is that before everything was symmetric, and now everything is going to be symmetric again. So if I'm standing here, the probability that I go up to this point up here is going to be the same as the probability to go down to this point up here. But now it's continuous and everything's mushed together, and I can get to any point in space. What I'll say is that, in general, using random walks Brownian motion is just one example of things we call diffusions in probability. It's a large class of stochastic processes. You can make the Brownian motion kind of faster in certain places than others. You can kind of make your Brownian motion tend to drift this way. It's moving randomly, but then something's kind of pulling it to the side. And you can get any of these kind of things from scaling limits of random walks, but there becomes pretty complicated when you want to have correlations between the two different directions. Like if I said that I wanted to get a Brownian motion where let's say it's something like this, or a diffusion that was like W1 plus W2, W1 minus W2. Okay. See, I'm considering a process like this. Right? So my diffusion matrix is something that's not zero off the diagonal. Okay? Then when I want to look at the random walk, it's not exactly clear because these two directions are correlated. How to do the stepping distribution, going up and right when the two things should be correlated and not independent. Yeah.
Sorry, I don't.
So I'm saying if my process, is some diffusion, or by what is this? 1, 1, 1 minus 1 times W1 xt is this matrix times. So I have two Brownian motions that are independent, but I define x as this matrix times those Brownian motions. And I want to find this as a scaling limit of random walks. You seem to somehow couple the distribution that I walk up and I walk right at the discrete level. And there are whole textbooks written about this. In fact, to get certain behaviors, it's only until recently, within the past 10 years, that people knew precisely how to handle all cases where the things were coupled and there was degeneracies in the coefficients. So like this gets really close to 0. This matrix has eigenvalues close to 0 and stuff. So if you wanted to discretize and simulate random walks, there could be all sorts of technical problems involved. But okay, for the case we were considering, it's all very straightforward. And so we want to show in the next 5 minutes the analog of the differential equation we had before. Alright, so what I want to show is one, if omega is bounded and open in Rg, and G is continuous on the boundary, and okay, the boundary has to be kind of nice, but I'm going to get into that. We're going to let T be the first time just the Brownian motion in the boundary of omega. So we're kind of starting inside. Now we have this continuous random walk. We're waiting till it to exit. Okay. and we're going to call that time t. I can't jump over the boundary because it's continuous. Okay. And u of x equals expected value starting at x. We're using the same notation where we start at x and we look at where the Brownian motion exits, and we and it gives us a value g, and we average all over all this probability. You know, this random process of where we exit. Then u should satisfy our version of our equation. Minus 1/2. Okay, this doesn't matter because we have 0 on the right hand side, but the generalizations of this is relevant. And u on the boundary is g. So this is the first thing we want to show. So let's go. I don't think I'll have time to anything else. So let's go and talk about this. So first thing to notice is, okay, intuitively, it's the same kind of problem as before. U on the boundary is g. If you start on the boundary, then the time that you exit should automatically be 0. But that's not exactly true all the time if our boundary is really ugly. So Brownian, if you make a weird cone in 2 dimensions, then the Brownian should have a positive chance of never exiting instantly, of just kind of instantly going inside the domain. So, okay. Under reasonable conditions, though, on the boundary, it's very intuitive that you. So this should be maybe is inside omega complement. Then the issue becomes more clear. Okay, under reasonable assumptions of this boundary, this should be clear. So really, all we need to show is this kind of averaging thing that for symmetric random walk, it was just that this operator meant you went up, down, right, left, all the same probability. That's the way you have this thing. So I don't know how to do this without at least one little fact about harmonic functions. So functions with Laplacian 0. So this is a fact. Maybe the first thing you learn in PDEs. Laplacian view equals 0. If and only if. Alright, U is continuous. And average over the boundary of any ball that starts centered around x of radius r that's contained inside omega. Let's get to U of x. Bx r contained in omega. So this is saying that it's called the mean value property. Harmonic functions are something such that the average around them is equal to the value at the point, at all points. You can take averages over spheres, or you can take averages over balls, and it's the same kind of thing. They have this symmetry in them. And to prove this is just using divergence theorem. It's the first thing in any PDEs book. And, this is kind of the main point is that the Brownian motion has the same averaging as the symmetry as the random walk. And so really, it's kind of like the mantra in most of this business, is that the reason the PDEs and the probability of the stochastic processes have this connection is because of the symmetries in the stochastic process are the same symmetries in the PDE. So that's kind of like when this PDE is, or when this stochastic process is kind of like the stochastic process for this PDE, right? It's because they have the same kind of symmetries. The simplest example is Laplacian has this kind of rotational symmetry, and so does the Brownian motion. And that's why they mesh so well together. And the other fact we need, which is less trivial, called the strong Markov property. But it's very intuitive. This is less intuitive, and this is less trivial technically, which says if S is less than or equal to T, are exit times. Meaning, this is the exit time when you exit some domain, and this is the time you exit some bigger domain. Right? Then the expected value starting at x of f of wt is equal to, here's the messy expression, expected value starting at x of expected value starting ws of f of wt. Okay. So this is exactly the kind of thing we said before, where it says, okay, I'm going to first walk until I exit from some domain, which is represented by, the exit time is represented by s, right? And then from here, I'm going to keep walking until I exit t, or the domain that's whose exit time is represented by t. So, and then I'll average over all these paths. So it just kind of says that, once again, I don't care where I walked before and then I walk afterwards. You know, it's all the same in the average. That it's kind of like another result of I don't care what happened before. All I care is where I was when I exited. I don't care about how I got there. So these are the two things that we're going to use, and then it'll be very fast. Okay, where did I put this? Yeah? Okay. So, one line, then we can all go home. Want to show expected value x f of w t is harmonic, meaning Laplacian is 0. I'll call this u. Laplacian u equals 0. So we want to show this mean value property, and we shouldn't erase the problem, but just go with want to show mean value property. So let tau br be the exit time, or let me just say let s, let's call it s. From ball centered around x with radius r, which is contained in omega. Okay. So now, obviously, you have to exit this ball before you exit the domain omega. Thanks to this. Right. So this will satisfy our strong Markov property. Expected value of f of wt. Right. We just follow our nose. Expected value of ws wt. And so we're taking the average over all exits from the ball of the location, right? And then we see where we exit from that location at the boundary of the ball. But the question is kind of like, what's the distribution of the exit from the ball? Right? If I have a Brownian motion and I say that, where am I going to, what's the distribution of me exiting from this spot on the edge of the ball at this spot? Well, the whole point is that the Brownian motion doesn't favor any directions. So the distribution will just be the average value on the ball, right? Distribution is going to be uniform distribution on the ball. So this is just going to equal the average on the ball of expected value y f of wt d sigma y. This is just the surface measure on the ball. All right. So this is just exactly. Yeah. Right. This is exactly this thing over here, which is just the average boundary of u of y sigma of y, which is just a numeric property. So it all really just came down to the symmetry. Most of the time when you prove things like this, you use this big hammer called Edel's formula. In fact, from what I've seen, most of stochastic calculus is just using this thing called Edel's formula in clever ways, which is kind of like fundamental theorem calculus. I guess you could say all of analysis is just complicated uses of fundamental theorem of calculus, so it's not really saying anything bad on stochastic calculus. But that makes all of these calculations really easy. But okay, I wanted to say symmetry is what's kind of interesting for me as philosophical connection between these two things. Alright, so I rambled on. Thanks for listening.
Any comments or questions?
Yeah.
So you sort of hinted at this, but like, so, like, obviously, like, this should, like, you can probably do more general parabolic and elliptic type
Mhm.
things, but is there, so like, the direction in which this stuff generalizes in terms of, you know, I suppose nonlinear PDEs and stuff, like, is there, like, a particular?
People do stochastic representations for nonlinear PDEs.
Yeah, yeah.
But the story isn't as nice as this. I mean, the generator for any Markov process, right, is a linear PDE. So the nicest cases, right, when the thing you want to consider, right, the stochastic process has this natural PDE associated to it in the most basic way. You know, it's all for linear problems. But, you know, well, Gautam's got results about doing Navier-Stokes with, doing things about Navier-Stokes with stochastic processes, so you know it's out there, but I don't know how common the work is. Yeah.
So I'm going to ramble briefly and then just ask if my rambling is relevant.
Yeah.
It might be irrelevant.
Yeah.
But, so think about random walk on just a discrete one dimension. I pick a point anywhere with probability 1, I will hit this point eventually.
Mm-hmm.
Same thing in dimension 2, but this fails in dimension 3 higher.
Right.
Does that notion have any relevance in like
This
trying
is
to
like,
bump up the dimension, or like
You're saying with making the
with going to continuous?
in the continuous Brownian motion, they have all the same kind of analogous results.
Okay.
Right. All in fact, these are like standard exercises that you're.
So how do you actually phrase? So like in 3 dimensions, for instance.
So in 3 dimensions, you kind of say that you have a ball over here. So your probability hitting a point in 2 dimensions is 0.
But you can hit the ball with
But
probability.
you can set any probability, any ball around the origin, you will hit it with probability 1 eventually. But in 3 dimensions, you can put a ball around the origin. If you start out here, you only have some finite probability that's not equal to 1
Okay.
that you're going to
Interesting.
return. So you have to give it a little bit of volume, but you get the same kind of recurrence results. And very similar proofs, in fact. You can
Okay.
do the same kind of proofs if you want. But they're even slicker proofs with stochastic calculus because we can just relate it to PDEs.
Yeah,
Pretty
because
easily.
instead of like summing, you can just like integrate.
Yeah, it becomes actually a lot of things become cleaner in this case. Yeah.
So, are there like equations that you can solve like with like these methods that you cannot solve with other tools?
I actually don't know any examples where you can solve a problem. The problem was first solved using probability. I don't remember ever hearing about an example where you have a PDEs problem. Because there's been a lot of examples where people found easier proofs for things that were solved a long time ago, or better explanations for things that were solved a long time ago. But you know, there were some heavy hitters in PDEs in like the 50s. Georgi and Moser like shredded together parabolic theory, really good estimates on solutions in very general settings, and so it's pretty hard to bump it up. But you find much easier proofs using probability. So maybe if the probabilistic perspective existed much earlier, you know, it was first even barely started to develop in the 30s with Cohn. Maybe if it existed longer, probability would have beaten it out. But I don't know examples
That's
where
one-
it's necessary to use this.
Galton was working on something in PDE. He found proof in probability, and he didn't find proof in. So
Well, you're saying he has a result that's
yeah,
like a paper, you're saying?
yeah, paper,
Okay. I don't know what it is now.
something about homogenization. So
Yeah, but I think that's a probabilistic. It's a probabilistic result, really. I think he's looking at stochastic differential equations.
but that's it's a parabolic equation that he was looking at.
I don't know.
So
He knows. Son knows.
No, I mean-
Got him, nailed it.
yeah.
Alright, let's pass it again.
have a more technical talk in my back pocket that I'm going to pull out later this year. For those hardcore probabilists that want to see some much more interesting stochastic representations, actually for a nonlinear PDE. Yeah. Slightly a little nonlinear.
It's not highly nonlinear.
No, it's just a little nonlinear. So just add a little U to something small.